Hello, my name is Alexandros Kouris. I'm from Imperial College London and I'm here to present your recent work on self-supervised CNN-based autonomous drone navigation. The current state of the art in learning-based visual navigation employs either end-to-end imitation learning methods that provide a direct mapping between raw input images and control outputs, or learning-based perception techniques combined with rule-based hand-engineered motion planners. In the latter setting, the most approaches employ a binary classification algorithm to distinguish between traversable and non-navigable space. Our approach moves from inferring discrete action affordances to a more information-carrying prediction of the actual distance to collision towards multiple possible directions. These predictions are fused to a single navigational affordance vector, which is used to control the drone's motion. Of course, to train a deep neural network for a task like this, you normally need tons of data. In this work, to automate data collection and annotation process, we mounted distance sensors on our drone and let it fly around our campus on its own, using its external proximity sensor readings to label each captured frame and to avoid collisions. Having collected a large dataset of more than 300,000 distance-annotated indoor images, we train a deep neural network to predict these distance values from raw RGB inputs rather than using dedicated external sensors. This allows our method to be applicable on any commercially available low-cost drone equipped with a forward-looking monocular camera. The proposed model consists of a two-stream feature extractor that simultaneously processes the current and previous input frames in order to extract spatial features like visual appearance, which are then fused into a single stream that extracts temporal features such as relative motion. A regression unit in the end is employed to predict a continuous value that corresponds to the actual distance to collision. As you can see in this video, three distance predictions towards diverging directions within the camera's field of view, shown on the bottom, are fused by a local motion planner to a single traversability vector, shown on the top right. The angle and meter of this vector are used to modulate the drone's yaw and linear velocity respectively. Our approach can be used in a standalone setting to perform navigation towards the most traversable space for tasks like autonomous exploration or mapping, or to perform obstacle avoidance in combination with a global motion planner that handles the task of navigation. Our experiments demonstrate that this regression-based approach allows the local motion planner to make more informed action decisions in various situations compared to state-of-the-art classification-based or end-to-end methods. I'm really looking forward to sharing more results with you in the interactive session on screen number 4. Thank you very much.